let's consider a function f, which is analytic at z0 and in a disk of radius r centered at z0. So that it's analytic on and throughout the interior of this curve C. All right, of radius capital R. The point lowercase z lies inside this disk. And so for that reason, we can use Cauchy's integral formula to give us an expression for f of z. 1 over 2 pi I loop integral f of zeta divided by zeta minus z d zeta. All right? Now, what we're going to do next is truly astounding. All right? I subtracted z0 and then I added it back in. Now what I'm going to do is pull out zeta minus z0. All right? So I've got that. I made it minus so that everything is beautiful. Now what I'm going to do is recognize that the modulus of z minus z0 is smaller than the modulus of zeta minus z0, and that's because z lies in the interior of this disk. So I'm going to view this as the sum of an infinite geometric series. All right? Now, I don't want to do this in a sort of wishy-washy way. So what I want to do is I want to change this into a finite sum. So I'm only going to sum up to n. And then I'm going to introduce the sum from n plus 1 to infinity. So this will be
So z is a point where the function is not analytic, right?
the function's analytic at z. The reason that this is not 0 is because zeta minus z is 0 when zeta equals z. All right. So now I've got that plus all right, and then this is going to be the sum n plus 1 to infinity. All right? Now, this is a sum over finitely many terms. So I can unapologetically exchange the order of summation and integration in this term. So I would say k equals 0 to n, and then it'll be one over 2 pi loop integral over c f of zeta divided by zeta minus z naught to the k plus 1. And then it'll be z minus z naught to the k all d zeta. And then I've got the rest. That's an infinite series. It does converge 100% because the modulus of z minus z naught is less than the modulus of zeta minus z naught. But I don't like this infinity in there. It's wishy-washy. So what I'm going to do is I'm going to resum that series. It does converge. It converges to first term divided by 1 minus ratio. All right, first term, that's z minus z naught divided by zeta minus z naught to the n plus 1. Divided by 1 minus ratio d zeta. All right? So cleaning all of this up, we recognize z minus z to the k is independent of zeta. So that means that I can write f of z as the sum from k equals 0 to n this piece, which looks a lot like a coefficient, we're going to call it CK. All right? That makes this piece a power series. And then we're going to add this correction term. All right, what we got? When I distribute this, it's going to become just zeta minus z. And then I'll have zeta minus z naught to the n plus 1 d zeta z minus z naught to the n plus 1. So here, if you like, actually, let me put this z minus z naught inside. I think it'll be better there. All right? Here we've got a series. And if you recognize this, this is CIFFD, Cauchy's integral formula for derivatives. Remember, the k derivative of f at z naught is equal to k factorial divided by 2 pi I, integral over closed loop f of zeta divided by zeta minus z naught to the k plus 1 d zeta. So this is really just
Oh my God.
huh, that looks familiar. And it's going to be just like that. So this gives us an exact expression for f of z as a finite Taylor series truncated at n plus an error piece. This is the exact error in cutting our Taylor series approximation off at k equals n. Now, like any good complex student, we are now going to use integral bounds to bound this error. Let's see what we've got. We assumed f was analytic, so it must have a maximum on the circle. Let's call that maximum m. The modulus of z minus z naught is this distance, what I'm going to call lowercase r. All right, so the error in modulus is less than m over 2 pi, and then I've got r over capital R to the n plus 1 2 pi capital R for the length of the contour, and then 1 over zeta minus z. The modulus of zeta minus z is always larger than or at best equal to r minus lowercase r. All right? So cleaning it up, we get that. Now, since lowercase r divided by capital R is strictly less than 1, taking this to a large enough power will cause this contribution to become as small as we like. So for that reason, the error tends to 0 as n tends to infinity. And that gives us a firm proof for the Taylor series expansion centered at z0 for our function f. Note, to go back through this, the only thing we needed to be true of f was that it was analytic at z0 and on a disk centered at z0 containing z.